Welcome to the Gravity Engine mini game that demonstrates free return trajectory calculation. There's now a new scene in Gravity Engine 2.3 in the Scenes mini games folder. There are two flavors of it. There's the free return scene, which is the one I'm showing here, and there's a free return moon scene, which does essentially the same thing, but in units suitable for Earth orbit and the Moon with that unit system selected. So let's first of all just do a quick look here. So the point of a free return trajectory is to leave the Earth with a single maneuver that will lead the spacecraft to loop around the Moon and then return again to the vicinity of the Earth. So there's really three stages to the flight. There's the outbound ellipse to the Moon, there's a hyperbola trajectory around the Moon, and then there's a return ellipse from the point where you depart the Moon's sphere of influence and come back towards the Earth. And there's no guarantee that you go behind the Moon. There are free return trajectories that pass in front of the Moon, and there are trajectories that don't take you back anywhere near the Earth. The approach taken in this code is to do this as described, so as three different conics. So an ellipse, a hyperbola, and an ellipse. Eventually, I want to implement a mechanism where it's an actual three-body simulation, but here what you have are a series of two-body simulations. And that means that when you actually evolve it using three-body physics, the results will be slightly different because this approach is an approximation. There are some other simplifying assumptions. We're assuming that the orbit around the Earth is circular, that the Moon is moving in a circular orbit, and that everything is in the same plane. Again, assumptions that I'll relax as I get more nuanced calculations done in the future. In this particular scene, there are some controls you can use. You can control the point at which you depart Earth orbit, the angle at which you arrive at the Moon's sphere of influence, and the time it takes to go from the Earth to the Moon. In the earlier version of Gravity Engine, there was a patch conic transfer to the Moon, and it used a Hohmann transfer, which is the most efficient transfer to the Moon, but it means that it takes something on the order of 2 weeks to get to the Moon in the case of the real Earth-Moon parameter values. Typically, you want to get there a little faster than that because in the case of the Apollo program, it meant carrying too many supplies, being in space for too long. So if we go ahead and try some of these key presses, it says here KL to adjust the arrival angle. So you can see here as we move the ship in very small steps at the arrival angle, the return ellipse changes quite dramatically. It's a pretty significant change. We can also change the Earth departure angle by using the A and the D keys. It's somewhat less sensitive to that. And then if we use the S and the W, we can adjust the time of flight. So if we try and get to the Moon just a little bit faster, it puts us on a very different path around the Moon. In terms of how this is constructed, what's happening is that there's a single initial maneuver where you fly out, and everything else after that is just the evolution of the physics. So if we go ahead here and press X, the code takes into account the fact that the Moon is going to move. The Moon is over here. It adjusts the departure angle for that. We can speed things up a little bit by pressing the 3 key here. Now remember, this is now a true three-body simulation, so it will differ a little bit, and in particular this encounter where it loops around the Moon is the point where the most numerical instability or step size precision occurs. So in fact we didn't end up on quite the same orbit as we expected, although we do end up coming back to the Earth. In terms of what the code does, if we just have a quick look, there's a transfer calc controller class that you can see here on the transfer controller object. It links into the spaceship in the scene and a couple of additional spaceships which are used as anchors in the demonstration part of the code. And the orbit transfer calculation itself is perhaps not as much code as you might think. We create a Lambert universal to transfer to a particular point on the sphere of influence. We figure out what the velocity would be at that point. by getting the final velocity. We set our Phantom spaceship that's at the SOI with that velocity, and then further down in the update code, there's some code here to just update the hyperbola, figure out where you exit the hyperbola, and then work out the velocity at that point and update an ellipse predictor based on motion around the Earth with yet another Phantom ship. So the net result is a step in the right direction towards a complete free return calculation. It's an improvement over the previous patched conic approach, which used a Hohmann transfer, because you can now more precisely control the point on the sphere of influence and the time of flight. But there's still more work to be done, which I'm looking forward to doing in future releases of Gravity Engine. Thanks for your attention.